Welcome back to part 3 of section 5.6, where we're learning about rank and nullity. A couple things to wrap up here. The first thing here is that if we have a system, AX equals 0, the column vectors of A will be linearly independent if AX equals 0 has only the trivial solution. So why does that make sense? Well, let's think back to 5.5. In 5.5, we saw that if we have a system, it will have a solution if and only if this is in the column space of our matrix. Or in other words, if the constants can be made as a linear combination of the column vectors. Okay? If it could not be made as a linear combination of the column vectors, then there was no solution. Okay. Now, obviously, if we're looking at AX equals 0, okay, then if X is the 0 vector, of course that's going to have a solution. But what we want to do is see if it has any other solutions. So we're going to check to see if this guy has any other solutions, but AX equals 0 is just principally the null space of matrix A. But if the null space of matrix A is simply the origin, namely the 0 vector, that's the only way you can do it, then the only way you can make that is 0 of column 1 plus 0 of column 2 plus yada, 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 plus 0 of column n vector. Okay. Then, if that's the only way, then by definition, they are linearly independent. Okay. However, the null space doesn't always have to be just the 0 vector. If the null space is not just the 0 vector, that means we're going to have infinitely many solutions. And that means, like we saw in some other problems, that if the null space is not just the 0 vector, we'll have not just one solution, but we'll have infinitely many solutions. And that happens because one of the column vectors can be expressed as a linear combination of the other guys, so he is unnecessary. So hopefully that's made sense. Okay. So now, last thing here, we've been studying our theorem. It started back in chapter 1. So if A is n by n, then A is invertible. And that is going to happen if and only if the reduced row echelon form of matrix A is the identity. And we saw that A can be expressed as a product of elementary matrices. And our theorem grew and grew and grew. Okay, we get a couple new things now, other ways to say that your matrix is invertible. They are different ways to say the exact same thing. So if the rank of matrix A is equal to n, that's another way to say or know that matrix A is invertible. If you say that the nullity of matrix A is 0, that means the null space is only the origin, and if it's a square matrix, the only way that can happen is if the null space is just the origin, so our column vectors are linearly independent. And if our column vectors are linearly independent, that means on a square matrix that the row vectors are linearly independent. And if we have n linearly independent row or column vectors, then those row and column vectors will span all of Rn. So really cool how this is all finally coming together here at the end of chapter 5. So we'll see you in the next video for chapter 6.1.